Welcome everyone. We have a special guest today, Professor Blaž Likozar from National Institute of Chemistry, Slovenia, will be our guest today. I'm going to give the floor our researcher, Tülay İnan, to introduce Professor Blaž Likozar.
Thank you, Nokta Hanım. Hello, everybody. Welcome to Sabancı University Nanotechnology Research and Application Center online Nano Open Webinar platform. In this platform, we invite guests for academia and industry to share with us their knowledge and contributions. And today we have an important guest, as Nokta Hanım mentioned, Professor Dr. Blaž Likozar from Slovenia. Before the speech, I would like to say a few words about Professor Likozar. His expertise lies, among others, in heterogeneous catalysis materials, modeling, simulation, and optimization of process fluid mechanics, transport phenomena, and chemical kinetics. He is the head of the Department of Catalyst and Chemical Reaction Engineering at the National Institute of Chemistry and leading Chemical Reaction Engineering program. He is involved in numerous research projects, in total 50 Horizon Europe projects, and 15 of them are Horizon 2020 projects. He is also involved in many industrial projects, Total Energies, Evonik Industries, UPM, Novartis, Carbon Recycling International are just a few of the examples. He worked at the University of Delaware between 2014 and 15 as a Fulbright program researcher. He has published more than 330 articles and has more than 10,000 citations. He has H-index of 46. He is the recipient of Pregel and Zois awards. I should also mention that he is also our consultant on one of our recently started cost action project. Today, he has an excellent presentation for the participants on last decade's hot topic of hydrogen energy. And the title of the speech is Ammonia as a liquid hydrogen carrier of Initio multiscale catalytic synthesis, cracking reaction modeling. This presentation is also published in one of the high-impact journal of the Chemical Engineering Journal. Professor Likozar, floor is yours, please.
Thank you so much for the kind introduction and also for the invitation in general. So although, Tula, we have, let's say, activities or cooperation in another field, today, since my hands were completely free, I selected as the presentation topic the activities that we have related to ammonia. As mentioned as liquid organic hydrogen carrier, namely because many of our activities are related to storing hydrogen, also producing hydrogen, but then again also storing in a rather facile way. And this is definitely something that ammonia is an important part of. Today I will be presenting how we are tackling the catalysis and the reactor designing and optimization in silico, meaning from model, but I will also show you, because model without experiment is not really worth much, I will show you how this is then benchmarked and validated against experiments, and not just traditional experiments, but rather an electrified synthesis and cracking. So here in the presentation, you see where Slovenia is located. So our neighboring countries are Italy, Austria, Hungary, and Croatia. So we have a little bit of everything, a little bit of Alps, a little bit of coastline, karst world, and Pannonian plains. What you see there is Ljubljana, our capital city. With Ljubljana, it's a river and castle. And this on the right-hand side below is the institute. Okay. Now, if I continue with the scientific part. So ammonia is a hydrogen carrier. So why is it important? Well, the issues of hydrogen, although we all probably know that the hydrogen is quite looming, meaning that if we are to take decarbonization or defossilization, to be more correct, seriously, hydrogen will play an important role, especially in long-term energy storage. taking the renewables and the energy transition with a grain of salt. The main idea when going towards renewables is, of course, the deployment of renewables, meaning solar, wind, hydro. That's the first condition. Then the second one is, of course, smart grids. So managing the electricity without any transformation as much as possible. And only then, after the short-term storage with, for example, batteries, the hydrogen comes into place, especially for the industrial symbiosis examples where hydrogen can be used as feedstock. As you see here, the main selling point or advantage of ammonia is that you can relatively easily store hydrogen. So it's basically room temperature storage at a bit elevated pressure. So here it's written 10 bar, but it can also be less. So ammonia is at ambient conditions not that much volatile, especially if you fixate it, for example, in water solution or something like that. So the net reduction of, the net reaction of the production of ammonia is depicted there. And that's also the reason why ammonia is so interesting, because it doesn't entail the carbon cycle in its purest form. Of course, the way ammonia is produced nowadays with Haber-Bosch, it very much entails the carbon cycle, because the hydrogen is produced while reforming of natural gas. But as you see on the picture above, producing hydrogen from electrolysis, it is possible to synthesize ammonia quite nicely without the introduction of natural gas. So modeling and simulations, why even attempt them? So if we are looking at traditional Haber-Bosch, it's a highly integrated, large-scale, large-capacity process, which is extremely well integrated thermally and energy-wise. But it's also optimized to a very large scale of operation, which means that if we want to go towards electrolysis-based ammonia and decentralized ammonia also in the function of hydrogen storage, we have to think of new ways of producing ammonia. And one of these things is that ammonia has to be produced at lower temperatures and lower pressures at a, let's say, sustainable turnovers, which means, in effect, catalysis. And if we want to develop and understand catalysis, we have to go to elementary steps on catalytic surface. So this dissociative mechanism, besides associative, is the one that is very much relevant, or the main one for the ruthenium catalysts. And why is ruthenium important? Well, you know, because it's the only thing that actually works at, let's say, temperatures lower than 300 degrees centigrade. If we are looking at traditional Haber-Bosch catalyst, it does not contain ruthenium, but the temperatures are extreme and the pressures are extreme, multiple hundreds of bars. So the way we are tackling, for example, the understanding of the rate determining steps and how to then design the catalyst is to take various lattices, various clusters of ruthenium as a first approximation, and then we are doing the correlation of activation energies of all these reactions that I've shown beforehand, forward and backward, on catalytic surfaces for different ruthenium geometries. We are looking at reactants, products, but also activation energies. Here are examples for various of these reactions. So what we are getting at the end of the day, if we take this as a kind of snapshot for a specific lattice, we are getting first principles, which means without an experiment, parameterization of kinetic expressions for elementary steps, meaning adsorption of hydrogen, desorption of ammonia, adsorption of nitrogen, and then reaction of all the species on surface. Why the ab initio modeling is so relevant? Well, because in the first approximation, it does not need any experiment. That's the first thing. And the second thing is that basically you are able to discern quantitatively, with of course a margin of error, which steps will present a rate determining steps for your reactions. And this at the same time means that you, by means of model, you are able to visualize something that experiments, even if operando cannot give you. And this is the added value of, for example, DFT, to get especially the trends in reactivity and selectivity in the absence of possibility of experimental measurements. And here on the right-hand side, you just have the descriptions of how the reactions themselves are parameterized. Basically, what you are getting is pre-exponentials from vibrational and rotational frequencies, and you are getting activation energy from the difference in barrier, so the Gibbs free energy. Then the next step, of course, is microkinetics. You are doing the balances for your catalyst. So these are specifically, for example, for a batch reactor. If you are looking at a continuous reactor, which is typically the case for the synthesis, you are just adding the residence time term in case of steady state conditions and no axial dispersion. If there is axial dispersion, so deviations from plug flow model, this is considered as well. So this basically entails all the elementary steps for still one lattice of ruthenium. So this is an example here, how the activation energies are presented for different reactions, forward and backward. And this is, let's say, a kind of first, let's say, net result of what basically the first principles calculations give you. They show you, for example, how the unoccupied side, so this is the red curve, decreases over time. Mind you, the time is in logarithmic scale. And then you also see what's happening with all these individual species. And by means of this, you're able to discern, for example, what are the most abundant reaction intermediates, the body, and which are the rate determining steps. So in this case, you can clearly see, for example, it's the light green line, that the NH is the species that is covering from the ammonia synthesized surface quite substantially. And from the two graphs, you can also see how the conditions of the reaction, in this case, temperature, for example, can notably change not only the kinetics, but then again also the thermodynamics at extremely long times. Well, why are we doing all this? Well, first of all, to fundamentally understand how individual elementary steps on a simple ruthenium plane work. Then the next thing is what we are doing is we are reconstructing the nanoparticles with various lattices, various defects, various configurations. And all of this is relevant for us because we want to mimic a electrified catalyst that we are using ourselves. And when I say electrified, I mean induction heated. So why are we looking at, let's say, ammonia synthesis and cracking facilitated by induction? Well, there's two ways let's say, that there's two different sides of benefits. So the first one is that in essence, you're still capitalizing from all the advantages of thermal catalysis, meaning extremely high turnovers. You're delivering the heat basically by renewables, by means of magnetic induction. So that's the first thing. It's powered by renewables, but it's still thermal catalysis, which means extremely high turnovers. And for ammonia, you definitely need high throughput. The second thing is that on the other hand, or besides this, you are also delivering the heat exactly on place. If you are using traditional thermal catalysis, you will typically heat the reactor from the outside, which means that you will have a kind of thermal gradient within the reactor. For example, the Haber-Bosch process takes days to ramp up and ramp down where you are shutting off or turning it on. But on the other hand, in the case of induction, you are just heating the magnetic core. In this case, it was nickel cobalt nanoparticles that we are using. And this also means that the reactions is the reaction heat up and heat down is extremely fast. Here you see some micrograms of how the nickel and cobalt are distributed, so very finely. And this is, of course, put on top of aluminum. Well, if we then look at the whole DFT-based microkinetics, and we then parameterize our microkinetics and basically, let's say, align this with what we are observing experimentally, we see that there is, of course, with some regression of the parameters which are, let's say, the most non-critically determined. We see that we can come to a very nice agreement, but still knowing what's happening with all our species at various positions within the reactor. And this is an example for the ruthenium-based cracking within the electrified reactor. So with this case, we are basically having the parameterization for, let's say, all the reactions for also various ruthenium planes. And if we now look at how this is actually working, we see one of these key advantages that I want to leverage for the electrified or the induction-based synthesis and cracking. Here you see that the ramping up of reactor, which is, you can look it through the temperature curve, for example, which is the dashed curve, is achieved in a matter of minutes, which is extremely fast when you compare this to the days of to the time span of days that's used in traditional thermal catalysis. You can also see that the model predicted hydrogen and nitrogen production is quite nicely fitting to what we are observing. Of course, it's not a perfect fit, but what we are aiming for is first principles predicted behavior rather than have an extremely good fit. And the spike that you see in between is basically the desorption of ammonia from acidic sites in the reaction. So in future work, and this is something that we are doing for the time being, of course, is expand these ideal surfaces that we have towards the nanoparticles, which are a more accurate representation of what we have deployed on an electrified catalytic surface. And this is interesting because if we are doing, for example, TEM micrography of the catalyst particles, and we have a kind of population of these different nanoparticles, and we have catalysts with different distribution of nanoparticles, with different, of course, turnover of ammonia, we can then model-wise explain how all of these different ruthenium surfaces and all these different atoms are contributing to a kind of net effect that we are seeing along the lines of different selectivity or productivity. But of course, when you're parameterizing the microkinetics with DFT, you are still at let's say idealized level. Then, of course, the next step, and this is, I mean, here it's not under future work, but this is something that we've already done. It's important to also include the non-kinetic or non-thermodynamic limitations that are related to the synthesis and cracking. And this is specifically heat and mass transfer limitations, and also the limitations of flow. So for this, we are putting computational fluid dynamics to work. You will see some results later on. But here I want to showcase another thing that's quite important besides this catalyst tuning for a kind of decentralized ammonia synthesis and cracking. If we look at the synthesis itself, in case of commercial synthesis, what we have, since ammonia is like methanol synthesis, very much, let's say, thermodynamics limited process, meaning that you have a very low single pass conversion. Basically, what you want to do is have some kind of intensification, meaning that you want to go beyond the thermodynamic equilibrium that you have in a packed bed, and this is possible by many ways. So one is, for example, you have absorption, so kind of scrubbing of your product in situ, but this is difficult because temperatures are high, so you would have to have some kind of ionic liquids or something like that that's resistant but not harming the catalyst in this trickle bed. The second option is membrane intensified processes, which would basically take out the ammonia once it's synthesized, which is challenging from the CapEx perspective, meaning that membranes are quite expensive, and also it's difficult to have them super selective for the case of ammonia versus hydrogen, nitrogen. The third approach, which is actually the one that we are trying to address, is sorption-enhanced ammonia synthesis, which means that we are gradating our bed in a way that ammonia, once produced, is chemically absorbed onto the silica doped with metal halide salts. So while metal halides, because they represent the best trade-off between the scalability of the materials, because for ammonia we obviously need something that's not completely exotic, and also the function. So these halides are actually quite well working, mind you, at elevated temperatures that are inherent to the synthesis of ammonia. So we are talking about several hundreds degrees centigrade, which is the conditions at which normally adsorption is not favored thermodynamically. So this is the actual challenge we're having. From the computational perspective, and when we are looking at adsorption, and of course coupling this with the reaction, we're already entering the realm of mesoscale, which means that from the quantum mechanics, which you see there at the very low run of time and length scales, we are entering the realm of molecular dynamics and mesoscale, which means that we need to look not at DFT, but at molecular dynamics of the sorption of ammonia onto the materials that we are developing. So when we are comparing these two, well, it's the molecular dynamics are computationally cheaper, meaning that you can run a lot of them. They show the actual dynamics, which DFT does not, it just provides you the parameters. They can handle much larger systems. So we are talking about 10 to the power of 3rd, 10 to the power of 6 of atoms. But the drawbacks, of course, are that they are less accurate and that in its purest form, they do not entail chemical reactions. So if you want to have chemical reactions, you have to use reactive force fields, which is, at least for catalysis, not that straightforward. And on the right-hand side, you have an example of ordered silica, which is the one which we use to be a substrate for the metal halides, which are then used for sorption. So here you see an example of how metal halides are actually put into these pores of silica. Of course, we're talking still about everything in silico, so not experimental. So why would we even do that, both experimentally and model-wise? Well, we have a high ammonia loading capacity of such materials, but on the other hand, anybody working with metal halides knows that they are extremely highly susceptible to water. So there's an actual puddle of water that forms if you leave them on your bench top. The second thing, and this is something that needs optimization, is of course the sorption capacity after multiple cycles. So this is something that needs the most dire optimization. And that's why the silica is used in the first place, because basically it provides the stabilization of the metal halides loaded on top. So below you just have the description of workflow, and on the right-hand side how this is done conventionally. And this is like a nice representation of how these, let's say, molecular dynamics are actually done to find the optimal structure. What we are currently doing is having parameterization of metal halides, so magnesium chloride, manganese chloride, nickel chloride with reactive force fields. Then, of course, the reparameterization of silica for ammonia. Then using different pressures, of course, because this is important to have a realistic condition. And of course, then also look at various nanoparticles within this silica structure. Well, if we are then moving still higher on these rungs of multiscale modeling, we are coming to macro scale. So, which means, you know, what's happening not on mesoscale, but in a reactor, we are encountering mass transfer, we are encountering flow-related characteristics, and this is how it happens. So we're looking at pellet pores, we're looking at catalyst pellets themselves, and we are looking at packed bed reactors. This is an example how we are implementing the before mentioned microkinetics in CFD software. So basically we are doing the parameterization and then using not just residence time resolved microkinetics, which was the case before, but also space resolved microkinetics, which adds much more computational power needed to do the task at hand. So what you need for this in terms of mathematics or physics, well, there's obviously mass conservation equations, momentum conservation equations, meaning flow. There's energy conservation, where also the reaction enthalpy is encountered and the heat losses. And of course, you can use ideal gas formulation, or you can use some equation of state like Pink-Robinson or some other to have the high pressure corrections. And of course, the aforementioned species that I've shown all have to be considered in this case. The kinetics of ores being covered by the Arrhenius equation, the modified Arrhenius equation. With this, after the meshing, what you're getting is, let's say, the 3D kind of patterns along the pellets. And this is just an example for one pellet, but of course, then at some point, this is extended to hundreds and thousands of different pellets to represent an actual reactor. So I will basically conclude my presentation today with a kind of more broader overarching view on how we are dealing things, which ammonia is par excellence example of, but basically it's also extended to other such cases. So we are still in the very much so relying on, of course, experiments. We have multiple parallelized, either continuous or batch reactors to look at high throughput experimentation. It allows for fast experimental screening. It allows for systematic experimental design and online process analysis. So it's a kind of combination of experiment, and then you'll see also where the modeling pitches in. For the experiments, it's important that we have either operando, which is the most valuable, but also offline identification, quantification, and processing of data. And of course, with this, we can already speculate at mechanisms, which means intermediate pathways and reactions. So some we can speculate without experiments based on the chemistry and mechanism. Some we see from the observations that we get. The density functional theory is basically providing us with the parameterization of kinetics and the surface coverages and how the actual absorption on surface occurs. So we are liaising this with the characterization of surface, which means what kind of lattices we have, what kind of nanoparticles we have, what kind of surface composition and morphology we have. And this is, for example, something that we get from SEM, TEM, XPS, FTIR measurements. And with this, we are able to basically construct representative surfaces that we are using in modeling. Well, then, this simplified, let's say, frozen in space and time model has to be confronted with the realism of a reactor, which means the mass and heat transfer have to be included, sometimes for multi-phase reactions. Absorption, desorption have to be considered, and of course the reactions are surface in nature, which means kinetics and thermodynamic considerations to parameterize the model. If everything is clear, which is very rarely the case in the first iteration, we have a well-characterized catalyst for which we know exactly what is going on. We have structure-activity correlations, structure selectivity correlations. We have the whole mechanisms in place. And what is most important probably, are identifying the bottlenecks of reactions. So the reactions that actually need to be catalyzed. If the answer is no, which is, let's say, in most cases, the actual state of play, we ask ourselves whether we have enough measured data. If we do, we just return to the primary assumptions. So, did we assume everything, especially the mechanism and the reactions, in the correct way? And this is a kind of internal cycle. But typically what we see is that we will need more measurements, and that the initial design of experiments might have been lacking for some blind spots that we need to cover so as to have the whole mechanism in place. And this is a kind of methodology for catalytic reaction technique that we're using. Maybe just a few words considering the department. So this is a bit outdated, but still, at the time being, we are implementing 50 Horizon Europe projects. We have many PhDs and also various different projects. From the equipment side, we have basically everything that we need, not just for the catalytic reactions, but also, especially in case of biomass, we have a lot of equipment that is both scale up as well as allows us for the end use facilitation, which means fabrication of films, fabrication of composites. So we are doing, for example, recycling of plastics, and we are doing the bio-based chemicals and materials, but then we also want to validate them with some, let's say, final end use. And also from the characterization side, basically, we have almost everything in place. So some of the equipment might not be listed here because it's, as we consider it, infrastructural, like TEM, XPS, XAFs or such. But we have operators and we have the access to such equipment. Another interesting thing is that we are opening 2 new centers. One is for CO2 and hydrogen technologies here nearby the capital, and the other one is for biorefining. And especially for biorefining, probably is interesting because it's looking at a higher scale cutting-edge fractionation to high-quality cellulose, lignin, and hemicellulose sugar materials, but then also downstream valorization of these specific fractions. Okay, as mentioned, projects, they are not all listed here, but the general framework of the activities that we have is related to what I've been presenting today. So hydrogen production, storage, ammonia, liquid organic hydrogen carriers, then nexusing with CO2 capture either from air or from concentrated streams, various CO2 routes towards chemicals, so methanol, ethanol, syngas, BTX, but then also on the biomass side, fractionation, and then work with specific fractions, so either cellulose, lignin, and hemicellulose as biopolymer, or getting the sugars or the furanic or aromatic platforms out and then functionalizing them specifically. I think this is it in short. Yes, and with this, I would thank you for your attention. I'm basically concluding where I started with. So with our country, which is rather small, just 2 million inhabitants, with our capital, Ljubljana, which is also small, which has about let's say between 200,000 or 400,000 people. Depends also if you take the surroundings or not. And our institute, which as mentioned, is also expanding with 2 new centers, which are off-site, so not really in Ljubljana. And yeah, with this I would like to conclude, and I will leave the presentation on. If you agree, if somebody will have any question from the presentation, but otherwise also from the other activities that I've mentioned, I would very gladly answer any question that you might have related to the activities that we have, the methodology that we use, the equipment that we have at hand, and also the project that we have. This would be, yeah.
I would like to welcome Professor Blaž to Sunam and presentation. We are working together in one of the projects as a consortium partners. So welcome, Professor Blaž, and many thanks for your kind presentation.
Yes, very gladly. Thank you.
I have a question.
Yes.
You mentioned about high throughput analysis. Do you also use these analysis for characterizations?
Yes.
Let's say you have, I will ask very specifically. You
That's
have,
better.
let's say, biopolymers, and you extracted to them as lignins, cellulose, hemicellulose. And did you use high throughput analysis to determine the amount of these ingredients in the composition for screening?
Yeah. So we can, for the actual mass fractions, for example, we can use the high throughput fractionation. But if we were then to, for example, if you would be interested, let's say the difference in structural characteristics of lignin from these different, let's say 20 or 40 runs that we would have, this probably would not be possible to do in a high throughput manner, because you would need to have, let's say, carbon NMR, or you would need to have FTIR or UVVs or something like that. And I started with the most complex and then going to the easy ones. So for example, for IR, it's possible to have high throughput. This is not an issue. But if you want to have a very detailed structure of the lignin itself, so not just the mass fractions, this is typically not done. I mean, you're just preparing the NMR samples, and you are doing the phosphorus NMR or carbon NMR to see the structures.
If you have, let's say, infrared results for cellulose, lignin, and also hemicellulose for different samples, and if you upload these results, the convention, we use, of course, conventional methods to determine the amounts of these ingredients, and upload these results to the infrared. Of course, there should be a software to be used. And then can we measure the content of for unknown, let's say, biomaterials, the content of these ingredients as a high throughput analysis?
This was actually reported some time ago. Already we also applied this methodology in one of our national projects that we have, because obviously let's say wet chemistry fractionation is much more tedious and takes longer time than FTIR. But of course, it's not a perfect solution, which means that if you're doing the FTIR, there are always some deviations that arise on account of water content or the morphology of samples or something like that. So I would say like this, a very diplomatic answer. Yes, you can predict some trends. So, you know, if you're dealing with two materials, one is extremely rich in cellulose and the other one is extremely rich in lignin, and you are comparing them by IR, you will get the correct results in terms of, you know, which one has more of something.
Yeah.
But if you want to have an accurate result, for example, you are dimensioning some equipment that you have, and you want to have a very precise, let's say, amount of cellulose that you have, then it's always better to do it by the actual wet chemistry approach, so the batch reactor fractionation.
Okay, if I have one more question.
Yes, of course.
I wonder if we can use this modeling for also extraction purposes. How efficient to choose the methods, because you are using thermal induction as a best method for your case.
Well, you know, this is just one case. I would say that we use this thermal induction for thermocatalytic processes that need electrification. If you're talking about extraction of, for example, some high added value compounds from biomass, like antioxidants or something like that, I wouldn't say that this is necessarily related. But in this case, what I think is quite interesting, and this is something that we have been doing also, we have been applying model-based screening of solvents, and this was applied to ionic liquids and hypertactic solvents to see which one would perform best.
Yeah.
And this is, you know, it could be considered as one step beyond state of the art, because for now, what is mostly used is Cosmos software, which is mostly, let's say, thermodynamics based, entails, let's say, bonding and some thermophysical properties. But the DFT will give you a bit more accurate results. So I would say methodologically is a step forward, but still it requires a lot of work. So I would say, by analogy of before, so Cosmo-based approach for solvent screening, for example, for extraction, is the equivalent of FTIR. The DFT-based first principles modeling of the interactions of solvent is something like the actual wet chemistry fractionation that is needed for that. So that's a kind of analogy, I would say.
Okay. And one last question, please.
Yes, of course.
I'm worrying about your perspective about future process changes. What kind of changes are you expecting in future? Because we are concerning less water, less energy processes more. What's your expectations? I just wondered.
Yeah, well, I mean, what I always say with this kind of question is, of course, that I think that in general, as humanity, we would need to start to consume less. That's the first thing, because I mean, and this is the same with everything. If you look at natural gas, energy, if you look at plastics, the easiest way to produce less waste or consume less energy is to actually, yes, consume less. That's the first thing. And the second thing is, if you want to have things more integrated and circular, of course, new processes have to be developed. And not just, I mean, for example, we are mostly dealing with technological processes for either recycling of plastics, bio-based processes, but it's not just that. It's often just more logistic type of processes. I'm referring, for example, both to biomass and plastics, or if we are looking at renewables by that matter. So we are coming from a paradigm that's mostly working with very centralized energy and resource management, which is basically fossil energy, and this is basically fossil refineries. And we are now approaching the concept where we will have a very distributed energy harvesting and management, which is like, you know, renewables plus smart grids. And it's the same with resources. If we want to get our carbon from the recycling and from biomass, it's completely new paradigm. You know, in Slovenia, for example, we don't have a petroleum refinery because, you know, there's no need to. There's, you know, we get our oil from the one in Croatia, for example, or the one in Hungary. But if you're looking at a more decentralized manner, you know, we need to do something, for example, with our waste that we have in Slovenia, because the model that we have had before, that we are just exporting waste, it's not functioning anymore. We have to either combust it or valorize it in some other way. So I would say that it's a trade-off between consuming less, which is not the best model for the economic model that we live in, and of course the new technological and logistic processes for the new paradigm in energy and resources that we have.
Okay. Nokta Hanım, bir soru daha sorabilir miyim? I have one more
Hocam.
question. I have one more question.
Okay.
For the energy systems, there is fuel cell systems, also flow battery systems, redox systems. Which one do you see more future? Which one of them will be more used in the future? Yeah, this is what do you think?
I would say that probably a combination of both. This is a typical case with batteries and hydrogen. I mean,
Yeah.
and this is maybe something that I began with. So although we are heavily dealing with, for example, hydrogen electrolysis and fuel cells, I'm being very realistic. So any chemical change in energy transformation is generally unwanted. It decreases dramatically the round trip efficiency of an energy system. So the best way is to use electricity or energy directly. The second best things are smart grids, so that you manage within the grid and not store energy, if that is possible at all. And only thereafter, you know, there is a need for storage, basically. And this is what energy and electrolysis plus fuel cells actually are. It's energy storage in a way. And right now, at least how I see things in Slovenia and elsewhere in Europe, the idea is to have batteries for short-term storage and hydrogen for long-term storage. And in effect, you will need both. You have the short-term, let's say, short-term storage needs when you have a cloud coming over the sun, and you have a long-term needs when, you know, the summer is over and the winter is coming. So this is the two different time scales that you need to cover with renewables.
Thank you.
Is there any question? Dear Professor Blaž Likozar, thank you for your great talk. Thank you for your time. Tülay Hocam, also thank you for your contribution. Dear participants, thank you for your participation. We will have a special guest next week, Sultan Tepe, Nano Open. Let's meet next Wednesday.
Thank you and goodbye.
Thank
Thank
you.
you.
Bye.